Right, just saw that all presentations are now in uploaded, so that's good. So I think we can start. So welcome to the session on latest news and observatory reports. The section that we're running this afternoon will be the observatory reports section, part of the session. And tomorrow afternoon there will be the latest news part of the session. There are also slots there, so if you have some latest news to present, yeah, please let us know. But we're happy to give you slots. So let's start with this part of the session. So our first speaker will be Guayan from China, who will give us an update about the Megatu radio station.
Okay, good afternoon. I will talk about the latest progress at the Mian-2 solar observing station. Okay, with my colleagues. This is the outline. I will talk about the MUSA calibration and the extension of MUSA to the decametric wavelengths, as well as the development of IPS telescope. Okay. Yeah, for solar observation, we know that solar activities are the driving source for Swiss weather, and the radio technique can obtain unique information from the sun to the earth globally, like with radio observation as well as on the ground interplanetary scintillation. We can get all this information. So in Mian-2, it's about Inner Mongolia of China, about 400 kilometers northwest of Beijing. So about 10 years ago, more than 10 years ago, we built two radio telegraph array. And then in the past 5 years, it's extended to the decametric range as well as IPS telescope by the infrastructure project of China. So that's the previous existing telescopes, the MUSA low frequency, intermediate frequency in the decimetric range, the 400 megahertz to 2 gigahertz with 44.5 meter antennas and another 62 meter antenna covering 2 to 15 gigahertz. So that's the central part. But 3 years ago, the MUSA and the whole team, we moved from National Astronomical Observatory to the National Space Science Center due to the reorganization of the state key laboratories by the Chinese Academy of Sciences. And early this year, in May 2025, so the Ministry of Finance has officially approved the transfer of all the facilities from NAOC to NSSC. So at first, that's the logo stone of. Now it's changing from NAOC changing to National Space Science Center. So you can see that's the logo in Chinese, but now we moved but now we keep it as a museum to state the history of this observatory. So now this area will be replaced by the new logo of the National Space Science Center. Okay, so for the past data we already have with MUSA have this statistic results of the observation of the solar bursts, and it may provide a database for further study. And for the solar and non-solar dedicated facilities nowadays in the world, it's in an area for the imaging spectroscopy of solar radio. So the recent progress has been highlighted in Gary in 2023, the review paper, and also end of last year. So the decadal survey in the solar and space physics is highly recommended to in US to build this wideband spectral imaging capacity with the imaging capacity spectroscopy. So the FASA project is recommended with highest priority. So also try to image the solar atmosphere in 3D. So in his review, it's also pointed out that MUSA has exactly the right specification to perform high quality imaging spectroscopy, but we did meet some difficulty for the calibration. So then in the past, we also developed a new calibration method, as well as we added some big dish for the calibration. So we obtained a new formula for the point source calibrator if it's derived from the nominal position. So it turns out that from the interferometry theory, we could fix this deviation by theory. So it's turned out that now the calibration and the imaging can be carried out within the framework of the radio interferometry and aperture synthesis. So with this new technique, we can, for the multiple frequency obtained from MUSA data, we get better accuracy for. Then, as I said, at the same location, so we extend the MUSA, to the low frequency part, the metric and the decametric wavelengths. So we have this also the spiral, 3 spiral with 100 dipole antenna, log periodical dipole antenna, but the central part is already occupied by the north face. So we have now the central part in this place, and the calibration array, that's 124 log periodical dipole antennas. So now this is a bird view of the observatory. So that's both the new and the old one arm of the spiral. So you can see another one, and also for the newly established big dish for calibration of, and also the cylinder 140 long and 40 meters for IPS observation. So that's the bird view of the current situation in the Mian-2 observatory. Okay, so now we have 3 arrays located in this site. So that's the MUSA low frequency, 30 to 400 megahertz, and the intermediate band 400 megahertz to 2 gigahertz, and high frequency 2 gigahertz to 15 gigahertz. So with that's the same maxima baseline, but the antennas are distributed in these 3 arms. So for the calibration, that's the central part. So, okay. So since this already commissioning last year, so now we have for this decametric array MUSA-L, we have the daily observation. Here shows some examples. That's for the last year, the famous event for the solar activity, the May. That's our observation. during that period, there were many solar events. And last October, there was also happened many that have the Earth effect events. So we also observed, here shows one observation on the 9th of October last year. There were, in our case, at this 3 instance, we observed several the radio fan structure for the like a zebra pattern. With that, we could deduce the magnetic field during the burst. So, but it's interesting. We also, for this third one, we have both observation for the spectrometer as well as the MUSA. So we found with reduced, that's the observation, and this with high resolution of spectra and tempo, but the tempo similar, that's 5 millisecond, and here is 25 millisecond. But the spectra here is about 1 megahertz, and here 25. So we can see the middle one is just deduce this resolution with the same one, but from the high frequency observation, high spec resolution observation. So you can see they are similar. But then that's where impose a serious problem for the solar radio study. You can see the drifting tendency are different at a low resolution. That means people have to be cautious with the observation if not have the sufficient high resolution. But mainly the spectra, because both 5 millisecond and 25 millisecond, it's still similar high cadence, but you can see this frequency drift intensity are totally different. Okay, here show one example, type 3 burst, and for the last year, the April, so that's one event before the burst, but here you can see during the burst for one lower frequency, and here the same period for the higher frequency. So the burst. And that's mostly the event happens close to the sun. And yeah, this as I showed for the last October, there many space weather event happened, and we also observed type 2 and type 3 burst. So it's agree with the filament eruption, that's observation from SDO and as well as the Chinese ASOS satellite. So they agree to it. But from spectral, we saw similar type 3 and type 2 burst, but in the radio source, it can be seen different. Here, the source at 30 megahertz may reach more than 10 solar radius. So it's agree with the solar structure during that at that time. So yes, yeah, you can see that's the sun. So the 30 and source the high low frequency to high frequency, the high frequency part, the source close to the sun. So this just shows for one moment the whole source at the 30 megahertz to this high frequency, the close to 400 megahertz. So they extend more than 10 solar radius. That's okay. Actually, as I said, we wish to monitor the solar burst from all the way from the sun to the earth. So that's can be done on the ground with IPS telescope. The current facilities including the Wuti in India and Mexico in Mexico with single station, but normally with larger collecting areas, all the multiple stations like in Japan, Nagoya, with intermediate size. But now also from non-solar dedicated observation like here from MWA and LOFA, etc. That's also can. That's the picture for the Japan Nagoya ISEE. So they have three cylinders. Used to have four, but this is not working now. So now they also have three station. That's but the size about 30 meters long by 15 or 20 meters wide. For Wuti, that's 500 and it's large, 510 meters long by 30 meters wide. That's but it's a single station. So we proposed, okay, for IPS, it's by observing the different radio sources, so it can obtain the information from a different direction, and with that, to it's like the CT to reconstruct the 3D structure of the whole heliospheric space. So, but for the big dish, you can get observe the more radio source. So that means the reconstruction are done with high. But for the multiple resolution, you can get the solar wind results directly by measurements, but with less source, so it's rather sparse. So it's desirable to combine both. So that's the, okay, this is the, with the IPS observation, we can see from ground, that's the Wuti results. So can see how solar burst propagate from the sun to the earth. So we proposed a new concept that we wish to combine these features together. So we build with mainset, we have a big collecting area. So with the three cylinder of each 140 meter by 40 meter, but with three, so total collecting area bigger than Wuti's. But then we also have the subset with the parabolic 30 meter intermediate size, 30 meter parabolic dishes. So with the cryogenically cooled receiver. So with that, we wish, okay. With that, we hope we could combine them. This is a specification. Okay, so that's the site. The main site is in Mian-2. Another 2 is about 200 kilometers away from that's each have this 30 meter antenna. So that's the construction of this antenna. So it's built and functioning now. For the here I show some observation with different source. With that we can check this IPS observation. So the results are quite good. That's the at first light observation, and according to the literature, it's if the signal to noise ratio greater than 13 or 15 dB, it's okay. So for our results, it's above that value. I here show some result about 20 dB and 30 dB. So we have the daily observation. Here I just show one observation this June, so we can get the reasonable deduce for one direction, deduce reasonable solar wind speed. And we also use our telescope for the pulsar observation to test here show one result just with only 8 feet. We can have the pulsar observation. That's indicate our sensitivity agreeable with our design. Okay, finally, in summary, the MUSA with 2 array and plus the new one, we now have the 3 arrays available for the space weather observation, and IPS telescope were also constructed, and additionally with 2 30-meter dish in nearby counties about 200 kilometers away. So with this, they will play important role in solar and space weather studies. And IPS telescope may also be used for other targets, like the proposal to build a URSI network at a low frequency in Asia Pacific region. Okay, thank you.
Thank you, Yuan. We have time for one questions. So, yes, I don't open your microphone.
Thank you for the nice presentation, and it's good to see more of the low frequency telescopes coming up. I have questions. One, is the telescope ready to do URSI observations? In which case, we should try out some test observations at low frequencies. The other comment was you cut off at 400 megahertz, whether there's a chance that it goes to the normal radio astronomy EP band, 325 megahertz, because that is where most of the other low frequency URSI telescopes will be working, other than that band.
Yeah. Okay. For it's working now for the commissioning. It's also because it's a dedicated IBS telescope, so the bandwidth not that wide. We have like only 40 megahertz bandwidth, but at the 327 megahertz for the IPS observation. For IPS, we have 2 frequencies. Actually, we could have 3. It's one is 327 megahertz, and another is it's dual frequency, the 654. But only the bandwidth not that wide. And for the dish, we have the 3rd frequency. That's the L band, 1.4 gigahertz. So, but for URSI, we may need for the backend, we may need another receiver.
Okay, thank you. Let's thank Rob again. And we'll go to our next speaker, who is URSI from Fukushima in Japan. He's going to give us an update about the use of the Noyama from URSI.
Okay, nice to meet you. I'm Hiroshi Imai from Kagoshima University. So basically, some of the colleagues in Noyama Radio Observatory should come here to make a presentation, but because they are so busy, so instead of them, I'd like to briefly introduce a series of receivers in Noyama 45 telescope, and also myself, I'd like to focus on the VLBI system. So sorry. So now Noyama is so famous not only for the millimeter radio observation, but also the Japanese famous animation cinema recently. Yes, Detective Conan. Yes. So recently there are 10,000 visitors every month. So because of the forthcoming open day of the observatory, so we have to get ready for the preparation. So I also joined the open day to make a presentation for our activity. Okay, so I would like to briefly introduce a series of latest receivers in the 45-meter telescope. So you can see the optics of the telescope. So telescope has a Nasmith focus, and it has a big waveguide to the lower cabin of the telescope. So okay, so there are several receivers using the mirrors. One of the receivers can be selected. But recently, we can develop the frequency band selection filters to simultaneously observe 2 or 3 receivers. So this is a concept of the latest development. One of the concept. Okay. So I would like to briefly introduce the latest deep presented receivers in Nobuyama. The first one is where is the laser pointer? Okay, anyway, you can see the top left side of the receiver. This has 7 beams covering from 70 to 116 gigahertz, correspond to the ALMA band 2 and band 3. And this is in commissioning, but some preliminary images has already been obtained. The bottom right corner shows another new receivers covering the ALMA band 1 from 30 to 50 gigahertz. And yes, this is developed together with the colleagues in the AGIA in Taiwan. So this is today's topics I'd like to introduce to you. We are using the existing receivers already installed for a long time. And as already mentioned, in the left side of the beam guides system, we use 2 or 3 receivers at the same time by inserting the frequency band selection filter plate. And right panel shows some prototype for extremely wide band receiving system. Okay. So, sorry. So now I would like to introduce the left part of the system. So I give the name so-called Hinotori, hybrid integration project in Nobuyama triple band oriented. So this diagram shows the signal flows from the left upstream of the left side to the downstream in the right side. And you can see the 4 receivers covering 22, 43, and 86 gigahertz. And so, we can see the frequency band selection filters in the left panel. And in the right side, you can see the VLBI bank-end system, usually operational in scientific observation, and our new system highlighted in the blue color. So this shows the frequency band selection filter plate. So it has the 7 millimeter in width and 3 millimeter in width correspond to the different separation in the frequency band. So the left panel shows the frequency separation filters for between the 13 and 7 millimeters. And the right panel shows the another filters separating between the 3 and 7 millimeters. So they are inserted in the waveguard system in front of the receivers. So we can, as shown in the diagram, we can see, you can observe using the two receivers at the same time. In this case, we can now observe in 22 and 43 gigahertz at the same time. This is already being operational in the VLBI experiment. But this is a little bit different combination of the receivers. So in VLBI, we are using so-called H22 and H40 receivers. And this has already been scientifically operated. So this shows the 12-band simultaneous observation system. This will be this is now commissioned, and this will be soon open for the scientific operations. After testing the softwares to get the scientific data. And okay. So I'd like to comment on the VLBI backend system. So recently, we have the problem in the Russian hydrogen laser frequency standard. But fortunately, some part of the power panel, some part of the power supply is provided, fortunately. So therefore, now hydrogen laser frequency standard is active, and we have already conducted the fringe test in VLBI. So in 22 and 46 gigahertz. So this is now be operational in the East Asian VLBI network. And we are still using the recording system at the rate of 4 Gbps, and this is the option now regularly used in the VLBI network. But we have to need the frequency, data conversion from 4 Gbps to 1 Gbps to make a compatibility with the other stations. And so we are now testing the new VLBI backend system with the combination of the Octat AD sampler and the new recorders, so-called Octadisk 2 and VSREC. This is used for example, in the Event Horizon Telescope experiment, I think. So finally, we would like to achieve the recording rate at 48 Gbps to simultaneously receive the signals from three frequency bands in the dual circular or linear polarizations. And but in VLBI, we have some problem in the correlation between the circular polarization and the linear polarizations. But recently, this cross polarization correlation can be overcome in the software. So we will need to make some tests in the software. Anyway, we would like to make a fringe test in such a configuration in the Japanese with the Bella at first, then other telescopes in overseas. So, but in that case of the international baselines, we have to check the compatibility of the data format. Even though nowadays we are using the so-called VD format, there are some differences. I don't know where, but so we cannot obtain the fringes yet between the Japan and South Korea. So we have to carefully make a fringe test. This is our current status. So finally, I'd like to show our latest development, so-called nocturnes, to extend the simultaneous bandwidth from 18 to 190 gigahertz. This may be built in the HEMT amplifier, and the combination with the frequency selection, frequency band selection filters, as already mentioned, like this. But we need some development in the waveguide and feed and so on. So this is still a conceptual design. However, some of the this concept has already been tested, as shown in the next panel, next slide. So this system is a prototype of the wideband receiving system to cover from 18 to 58 gigahertz and in the room temperature. And this is now operational even in the room temperature. And we have already got the fringes, invariable fringes, in the 2 frequency band in the covered frequency range. And but we would like to cool that system in the new project. So this kind of the ultra-wide receiving system is aiming to make a spectrum for the Earth's atmosphere. So this shows the basic concept. Okay, this is basic concept of our spectroscopy to cover the spectrum of the Earth from the water vapor, liquid water, and oxygen, and so on. So this is very useful not only for the meteorology, but also the high pressure astrometry, where the VLBI fringes are so fluctuated due to the atmosphere, especially the troposphere. So we would like to monitor the precipitated water vapor in accuracy better than 1 millimeter. Okay, that's all. Thank you so much.
Any questions for the question? A question myself. So you mentioned VLBI. Is there also any plans to include the Novia telescope in the EAC observations?
Yes. Yes. At first, we would like to include the Novia to the current EAVN observation in 22 and 43 gigahertz. Then we would like to conduct the VLBI experiment in 86 gigahertz. If this is operational, then we can make a fringe test not only in the EAVN but also other telescopes such as JCMT and Greenland telescope and so on. This is our planned hope.
Thank you. Any other questions? Please wait for Michael.
Councillor Roshi, you mentioned in your talk that you had a Russian maser that you restored in 2025, if I understood.
This was it failed at first. Then we obtained the part of the power supply, some part. So this is exchanged by a Japanese engineer following the instruction.
Okay. Okay, thank you.
Thank you. So let's thank Hiroshi again. And, move on to the next speaker, which is Stephen Noglu, who is going to give a presentation that falls into the category of the open part of the session. Let's do it. Anomaly detection in, you could say, survey, which is using machine learning techniques.
Yeah, thank you very much. Yeah, my name is Steven Dungu. I'm a PhD student at University of Stellenbosch and University of Groningen. So it's a kind of a double PhD program. And basically my project title is developing computer-aided algorithms to help in image processing, ideally, like the end part of it, which is quite interesting looking at the latest developments that we are seeing, and especially the updates that I've been seeing through the conference. So I'm presenting one of the works that we're doing, and this is on anomaly detection. It feeds into other workflows that we've done before. I'll maybe briefly highlight as we continue. So the motivation for this is ideally detecting anomalies or radio galaxies within the radio astronomy space is quite challenging, considering there is a lot of data that is being generated each and every second. But then there's a lot of rarity of the labeled data set. So ideally, when you're training machine learning algorithms, we want to have the labeled data set. So we have very few samples of that. Just a minute, sorry, take note of time. So another thing that is also important is, we also have a lot of technologies coming in, especially from the computer vision technology and pattern recognition. However, most of those methodologies that are there, quite good, excelling very well, but they also come with a cost of requiring a lot of resources, especially in compute terms. So for us, ideally, we are looking as a gap in the sense of we want finding an approach that will be efficient, number one, and also would require minimal supervision. So require just a few labeled data sets that we can utilize. So for us, we have a proof of concept based on our methodology. And on this regard, we've used a data set that is already available as a benchmark to prove our concept, as a proof of concept for what we are proposing. And in this case, we have a data set that, as you can see the distribution, it has two categories of normal sources, and this is the FR1 and FR2s. As you can see, this is how the structure looks like. And then we have two types of galaxies that we consider as anomalies. In this case, they are mainly ring-shaped, and some of them are X-shaped. So in this particular data set, so those are the kind of anomalies for this case. And then I'll also show the third column, another set of anomalies that we created ourselves, and this I will explain later on, because it's ideally just to help us in making sure that the pipeline that we are developing is not, there's no data leakage ideally, so at least the validation process is sound and valid. So how we create it, just to give a preview of that, is we take the existing training data sets and then do some augmentation, and then ideally we get the images and then try to flip them and then superimpose them to combine them, so that at the end of the day, you have two galaxies, combine them. So after combining them, it comes, of course, with a new galaxy type that will definitely not be conformed to the normal galaxies that you're working with. So this is just to cover the challenge that we don't have sufficient labeled data sets. So it creates some anomalies that, of course, well, you cannot envisage, you will not be expecting, but ideally this is the purpose of anomaly detection, because at the end of the day, we want to detect galaxies that we've not seen before. Just like the odd radio circles that was discovered the other day from the MICAT. Just to give a preview on this state of the art of the data set that I just showed. So there's a published paper on this workflow, and they have quite good results. They did quite extensive experimentations on that, and they used quite a number of autoencoders, which is kind of like, I would say, the state of the art. It gives the state of the art performance in most computer vision techniques. And with that, based on their performances, they recorded a G-mean, and this is just an accuracy metric, which kind of balances between accuracy of normal galaxies and accuracy of that of then anomalous galaxy. It's quite important because it helps to take advantage or capture the fact of if the data set are imbalanced, accuracy will not be a good measure. So G-mean gives a balanced assessment of the performance. So it won't give a biased view of the performance of that algorithm. So now, having explained that, the data set and that, I will explain the methodology that we are applying for this purpose. So one is called trainable crossfire filter. So this is an approach that ideally works like classical computer vision techniques. And mainly its aim is to detect, if you give it an image, its aim is to identify or characterize whatever objects that are within that given that image that you provide to it. There are few characteristics about it, and that's why we find it to be an optimum and quite relevant for this use case particularly. So for one, we have tested based on our previous experiments that is efficient in terms of the number of flops that is required. From previous experiments we've had, like when you compare with deep learning techniques, it takes up to 20 times less computations, in some cases 14 times. So those are two previously published papers. So, and then number two, as I'm going to describe in our next slides, is the fact that it's explainable. It's easy to trace back and tell why did we give this as, why was this prediction given as this? So that is another thing that is important. And then the third point that is useful and very relevant for this workflow is the fact that it takes care of the rotational invariance. So we understand the telescope, depending on the line of sight, it could observe the same source but at different angles. So at least when you change the same image, we are still able to view it as one single source with the same level. So the 3 steps for how the process works. So that's how I'm going to explain the specific methodology that you're applying. So once you get to the source, I hope this works. Let's see. Yeah, so once you get the image source, like for example, this is an image source here. So the first thing is we apply a bank of center on difference of Gaussians. This is based on the second derivative of it is difference of Gaussians ideally. So for this case, we take 2 Gaussians, one with, let's say, sigma 1, and then sigma 2. If when you take the sigma 1 minus sigma 2, that is the difference of Gaussian. When it's positive, it gives us a center on, and when you convolve, that's when you get this resultant image. And then when you take the inverse to give us the negative side, this one here, so this is the response that you get when you convolve on a given image. Then once you apply that, the next step you do is to combine or superimpose the 2 resultant response maps. And then once you have this, so the first thing is the difference of Gaussians ideally acts as a band filter. So one need to help us identify the sources where they are. So you can see clearly from this, we are able to clearly see from this especially identify and capture the main components of the source within that image. So we're able to see the blobs where they are, the jets, and the core. So as we get this, so the next thing is we want to extract the feature or the salient features that we can use later on for the downstream tasks. So for this particular case, what we do is identify like a point where most of the source is actually identified. So like for this case, we can identify this point as the center because the source is centered. And then once you identify that, so we apply a series of concentric circles. So you draw concentric circles around that. And this is just a systematic way of obtaining a numeric vector of values that we can use in the downstream tasks. So for this case, we identify as the center source. And then from after setting each, so for this case, I'm using 3 concentric circles specifically. So from that, based on the center and the points where you have the local maximum, so the points you see at the intersection, you see there are points that I've indicated there. I hope it's clear enough. So those are the points that we take as the salient features for this case. And by taking a series of these salient or the values that are conspicuous enough from that image, we record those values, and they are the ones that will characterize the structure of the radio source in particular. Once we do that, there are 2 things that we also add on top of that. And the first thing is to take care of the rotational invariance, as I said. So this galaxy could be of this case, but In another case, another telescope will take it, let's say, twisted at 90 degrees. So we want to make sure that the descriptors or the salient variable, the values that you're taking here can also take a consideration in case that source was rotated at an angle. So what you do is once you have obtained a descriptor value for this, we also take that value and take similar values at rotated angles. So we'll change this and take as, for, let's say, 7 angles within the same frame. Then once we've done that, we also add another thing that is important for this particular case it's the aspects of taking care of variations. When we are training getting the variables, we also want to take the aspect of tolerance in terms of the change of scale, because different galaxies would come at different scales. So introduce some blurring and shifting, and this is ideally to help us to take advantage of in case the scale of the different radio sources are taken into consideration. So once we come to anomaly detection, it's important to say that the feature vector that we would obtain from this, how it becomes useful in the pipeline or in the downstream task is the fact that so the responses that will be obtained from the configuration that we did for images that are of normal behavior, or let's say like what we have classified as normal galaxies, the response should be similar. But for those ones that, let's say, would come and it has a completely different morphological appearance, the response should be provided should be quite weak. So this ideally should now start creating the differences of you identifying between the two responses that you have, which one is of normal category and which one is, let's say, an anomaly. So based on the process that I described before, the objective at the end of it all is to create a numerical vector that would ideally represent the structural pattern in the image. That is, of course, as I said, rotation invariant, and also it's also take care of the variation in terms of scale. Then the feature vector that we obtain, we call in this case a feature crossfire descriptor. It's then used, so we kind of create it now becomes like a tabular format in this particular case, because one crossfire filter would create the first, let's say, first column, and then we create several, so that at least the combination of the different crossfire filters that you obtain, if you create like, let's say, 10 or 100, at the end of the day, they can help us create a signature of each and every image that you provided. So the whole pipeline is, I'll give it here. So you do the configuration process, then apply the configuration process filters for all the images. So what I didn't mention is when you're doing the configuration, we only use a sample of images from the training data set that we have. Then once we have that, a set of crossfire filters, from that is with what we apply to all set of images that we have, both for testing, validation, and for testing and validation, and also the training. Then we create the descriptors, which will just be numerical vectors for that. And then from that, we run normal machine learning algorithm for this particular case. We are using local outlier factor. And then using that pipeline, we now use it to perform anomaly detection based on the feature descriptors that have been created in this particular case. Just to give a preview of the performances and how they compare with the previous ones. If you look at the performance, so we're pretty doing we get us an accuracy of around 79%, and this compares to 77, which was obtained based on a deep learning architecture based on autoencoder. And then, so we also have another value that I'm showing here of 78. So the difference between the two is, one is where we use our own variation of images that are being based on synthetic. And this is to ensure that we are training the algorithm based on images that outlier that it has not seen before. So we're not using validating it on images that it will already see at the end of the day. Okay. So some of the limitations, it's important to mention this. So we trained it, this work was based on a small data set. Of course, it would be useful to see how it works out on a larger data sets like the MICAT or the LOFA data for this particular case. This is something that is already in pipeline to see how well if this can be scaled out ideally. And then as you see, the synthetic data set that we used, well, they may not capture all the oddities, of course, but as we explore actual data set, I believe this would help us even see how well this generalizes into real world. So a few things that we noticed from this and conclusions. So one, in terms of performance, we get at par and actually better performance compared to deep learning algorithms. And this is a paper that was published in 2025. So I believe it's quite a good thing to see that. The fact that we're also taking advantage of the algorithm in this case is computationally less expensive. As I said, in our previous experimentations that we did for like image retrieval, we had like 14 times less computational flops when you do the comparison, like doing the computations. So this is quite scalable in this sense. So it doesn't, when the scale of the data increases, so at least the amount of compute that will be required will be way lower if you're comparing it with what the state of the art is. Yeah, thank you very much. In case there's any question, I'm happy to answer.
Thank you. Are there any questions? So I have one. So does this method require any pre-processing of the images that you feed into each?
Yes. So for so for this particular case, since we are comparing with we are comparing with a methodology that was already done. So for the images that were provided and the data set is shared, so they had done sigma clipping for that particular case. So there was that step of pre-processing just to reduce the noise in the image. However, something that is also in the pipeline and to see how it works from other experimentations and works with crossfire filter, it's kind of quite robust even with the noise. So I'm pretty sure the performance would typically be around the same performance if sigma clipping was performed. Yes.
Okay, thank you. Any other question? If not, then let's thank the speaker again. We can move on to our next speaker, who is Jasland, who will give an observatory update about for the NCRA.
This going. Okay, so it's up there. Yeah. All right. Good afternoon, and I will be giving an update about the facilities at NCRA, and let's see the pointer. Oops, not. No, does this work? So is there something else to move the slides or just? How does one? Already.
Okay. You upload PDF. Okay. Here you can see what's on the screen.
Yeah.
Cursor, as you can
Just use this. Yeah. Okay. Thanks. So we done two large facilities: the UTI radio telescope and the Giant Meter Wave Radio Telescope. The UTI telescope is quite old, operational since the 1970, but it's still a very useful facility. And I'll talk more about that. We are currently reviving it to get it fully functional and actually upgrading it. And the GMRT, which was built in the 1990s and is open international facility since 2002,
and has produced many interesting results. And we did a major upgrade of that a few years ago. So let me start with the UTI telescope. It is a long cylindrical paraboloid, but it's an interesting thing. It's mounted on a hill slope equal to the latitude, and that makes it an equatorially mounted radio telescope. And over the years, it has produced many interesting results, all the way from cosmology to the interstellar and interplanetary plasma. And we heard Yuha talk about what it has done in terms of solar wind studies. And that's something that has been a very unique thing about the UTI IPS data, which has been used by the global community over the years. And we are now reviving the telescope. We did a thorough check of the various aspects, civil, mechanical, electrical, servo systems, and we fixed many of the issues which were mostly age-related. And I'm happy to say that the telescope is now almost fully functional, barring one or two RFI-related issues that we are in the process of fixing. And the receiver chain has been checked, and we are now ready to actually start using it, starting with resuming IPS observations and also pulsar observations. Meanwhile, there is an upgrade of the UTI which is planned, which is to go digital, to digitize the signals as early as possible in the receiver chain. In this case, at the level of 4 individual dipoles. So there are a total of 1,056 dipoles, and we will be digitizing and then processing the signals to produce 264 element interferometer with multiple beams, so that it can be used for many other kind of niche experiments. So this work is ongoing. There is a complete shakedown of the receiver system that's been done, and we are ready to start developing the final backend to do the processing. Moving on to the GMRT, which is one of the largest low-frequency radio facilities. It's located in the western part of India, near the city of Pune, which is where NCRA is located. And this was built in the 1990s and operational since early 2002 as an international facility. And there are lots of interesting results since we did the upgrade, and I'll talk about some of them, and also talk about some of the new features that we have been adding in the last couple of years, as well as the plans for further improvements. So the GMRT is an array of 30 antennas, each of 45 meters diameter. You can see a central compact array of 1 kilometer by 1 kilometer with 12 dishes, and the remaining spread out in a Y-shaped structure, giving the longest baselines of almost 30 kilometers. And after the upgrade, it provides almost seamless frequency coverage from 120 megahertz up to 1450 megahertz with a maximum instantaneous bandwidth of 400 megahertz. So it's got a very decent collecting area. And in addition, it has always supported both interferometry and the tide array mode since day one, which has really proved very useful for various kinds of science. And in terms of where it places vis-a-vis the other facilities around the world, you can see here that after the upgrade, the improvement in the sensitivity going from the blue dots to the magenta dots, and that makes it competitive with all the large facilities at different wavelengths, except of course the SKA when it comes along. It's been used by astronomers from all over the world. So you can see the pie chart here. It's a nice balanced usage. It allows for growth of radio astronomy in India with lots of participation of Indian scientists, while allowing for some of the best international projects to be executed on the telescope. So I'll show you some sample recent results, just a glimpse of a few of the things, starting with the continuum imaging. So this is a very interesting, nice plot which shows the capability of the GMRT at the low frequencies. So this is basically an initial pilot for what will become a large galactic plane survey, showing you how the GMRT data at the lower bands complements with the data at the higher frequencies and even beyond in terms of allowing you to get a nice matching coverage. From there, GMRT has played a key role in finding many of these large mega-size objects. And so on the left is an interesting one. It's a megaparsec scale jet, but in a spiral galaxy host, which is somewhat rare. And finding such objects is interesting. It probes important aspects of AGN feedback and galaxy evolution. On the right is something even bigger, 7 megaparsec black hole jet pair, which is perhaps the largest galaxy structure detected to date. So this is combined result from UGMRT, LOFAR, and the Keck telescope. And this has, again, interesting implications for jet formation and how jets grow. And in the early universe, as far back as 7.5 gigayears in this case. GMRT has always played a very useful role in understanding of galaxy clusters. And I show two results here, very recent ones. So on the left is the detection of a radio mega halo in this Planck cluster, which is perhaps the first mega halo discovered at frequencies above the LOFAR frequency, which then points to a new discovery space, which can be exploited by facilities where you can hope to find many more of these mega halo objects. On the right is a very interesting result on the El Gordo cluster, which is where you can detect a halo and a double relic mapped with the UGMRT. And this, when combined with the Chandra data, allows you to understand the acceleration mechanisms, and it actually produces some results which pose challenges to the current understanding of electron reacceleration. Moving from there to some results in H1 emission, which again has been a strong point of the GMRT. And this is a result where the furthest detection of H1 has been seen. This is by stacking in the deep 2 field. And what this shows is the detection of the emission from the stacked result with over 11,000 galaxies. But what is interesting is that it allows you to estimate the rate at which gas is being depleted. And it is an interesting challenge about how galaxy evolution happens at around the epoch of galaxy assembly. Moving beyond that to further higher redshifts, this is perhaps one of the highest redshift detections of H1 in emission. And it again points to the tip of an iceberg, which I think all the upcoming facilities should be able to produce many more new results in this kind of detections. Move from there to FRBs. GMRT has been very good in following up repeating FRBs. This is one example where we can track FRB signals all the way down to the low frequencies and study the frequency evolution. And this is a case where a large number of bursts detected, which show some evidence for chromaticity in the burst activity. And there are many other interesting FRB results, which I don't have time to go into. Finding new pulsars. So this is an ongoing pulsar survey with the GMRT, which has been quite productive and continuing to find more pulsars. The other unique thing about the GMRT as far as pulsars is concerned is the ability to study simultaneously at multi-frequencies by using the subarray mode. And this is a initial sample result of the same pulsar observed in two different bands, around 400 megahertz and in L band. And what this shows is the ability that you can get high quality data at different bands. And the way this has been used most effectively is to improve the precision of pulsar timing. And what you can do with this kind of data is to estimate pulsar dispersion measures very accurately and feed them back into the pulsar timing model to improve the time of arrivals and therefore the ability to detect gravitational wave background. And we all saw this plot from 2023, which shows UGMRT data in combination with the EPTA data to get this first tentative hint of the gravitational background signal. Since then, the INPTA, which is the Indian Pulsar Timing Array using the UGMRT, has gone on to improve the quality and the time extent of the data set. And we now have had a data release too, just a couple of months ago, where we've got now 7 years of UGMRT data. And what you see in the two plots below is an example of what this can do. So what you see on the top is the estimate of the dispersion measure as a function of time. And this is exactly the point that the dispersion measure varies significantly enough that if you do not correct the high frequency TOAs for this effect, you're likely to add additional noise in your timing. And what this shows is that with these widely separated bands of observations, you can get very good estimates of the dispersion measure and the variation. And so you see effect of interstellar medium in the left plot, and in the right one, you see the periodic peaks. These are due to the solar wind as the pulsar, as the Earth line of sight moves over the year. And so these are all significant corrections which have to be estimated and put in. And the bottom two plots show the residuals. The dark color, the black ones, are the residuals from the UGMRT L-band data, and the green ones are the residuals from the P-band data. And this combination allows you to get high quality L-band residuals after correcting for the interstellar medium effects. And this is something now there's actually work going on to do gravitational wave search on the INPTA data. So moving beyond that to the sun, there's been some interesting new results. And this is an example of the first robust imaging detection of linear polarization from solar bursts. And this is important. So this is something that was done both with the UGMRT and MWA simultaneously. And you can see very clearly the two different sources, burst sources, where significant amount of linear polarization has been detected very clearly for the first time. And this opens up a new phase in understanding of the solar radio emission. So I'll talk now briefly about some of the recent new features and ongoing improvements that we're doing at the facility. So one important thing that goes with all this kind of wideband data that is being produced is the ability to analyze it in terms of the pipelines. And so there's been a lot of work to develop pipelines that are fine-tuned for the UGMRT bands. And if you want to hear more in detail, you should go to the talk by Ruta, which is on the 21st, where there will be more detailed description of the pipelines which are mentioned here. So I will not talk too much more in detail, except to also add that some of this has synergy with our own contribution to the pipeline development in the SKA. So the other thing that we've gotten into is to get the VLBI fully running. And again, to this audience, I need not dwell upon the unique features that VLBI facility located at the longitude where the GMRT is would add to the global VLBI scenario, in addition to the high sensitivity that the GMRT brings. And a lot of this was described by Vishwesh in the talk yesterday. So I will not spend too much time, except to show that we've been active now, getting results with the EVN. This was the first VLBI image made with the EVN about 3 years ago. And we've done tests with different VLBI networks. This is the one with the LBA. done again over the last 2 years. We've been doing various tests and trying to understand any systematics. This is the L-band VLBI with the Usuda telescope in Japan. And what is more interesting is the ability to do a VLBI at P-band. Here's an example with the GMRT and the UTI telescope once it has been made operational now, and the Itate telescope in Japan working at 327 megahertz with baselines which are 900 kilometers and 6,000 kilometers, producing very clear fringes. Moving on, we now have a facility to record raw voltages from all the 30 antennas for 200 megahertz bandwidth, and the system to play them back and analyze them for different kinds of special signs is being developed, and soon we would have this running as an additional facility along with the regular interferometry and beamforming modes. We also now have a gated correlator that is running, the real-time gating that can be done in the visibility data for pulsar signals. And this is very useful for localization of new pulsar discoveries, as well as for things like studying off-pulse emission from pulsars. This is an interesting thing that was developed recently. And this allows you to keep the tide array phased even while you are doing your target field, as compared to going off to a calibrator to phase the array and come back. So this is what we call in-beam phasing. And this has now been implemented where, based on a model of the sky being observed, the results from the interferometer are used to continuously solve for the phases of the antennas and correct for those and keep the array phased. And this significantly enhances the usability of the telescope, both in terms of being able to use the further away antennas to the maximum extent, as well as to continue long observations without having to go back to a calibrator. And then looking ahead, we have now a very interesting new backend, which you would have heard about in a talk again yesterday, which is going to make the GMRT become a major player in the actual detection of FRBs. So far, we've been very good at following up the repeating FRBs, but this is going to give 2,000 beams over the 50% field of view and do real-time detection of both transients and also pulsars. And this is in commissioning now, and new results expected shortly. This is our aim to add complementary capability to the GMRT to go up to higher frequencies, up to 10 gigahertz. And again, Vishwesh talked about this in some detail yesterday, so I'll not go into the more details, except to say that work is ongoing right now to relocate 2 of these telecom antennas to the GMRT campus, and we hope that within a couple of years to have these fully functional and doing astronomy. There are also plans to expand the GMRT, either to add more antennas, maybe to double the number of antennas, and or also equip them with FPAs, and that's currently in the discussion stage to put together a proposal for funding. In addition to that, there's a lot of work that we do to coordinate India's participation in the SKA project, and I won't go into the details of that. So I'll stop here and leave you with a summary and take any questions.
Your thoughts, are there any questions for Desmond? If not, then in a short time, we move on to the next speaker. Will be Dr. Twok, giving us an update from the ATF.
Thanks, Stefan. Thanks, Yashwan. And I'd just like to as I guess one of the hosts of this meeting, and in a kind of a way, welcome everyone here to Sydney. It's great to have you all here in Australia for this meeting. Today I'm going to talk about the Australia Telescope National Facility. This is a facility that we operate which has telescopes around Australia that we offer to astronomers globally based on the merit of their ideas. And it's also the capability to develop new instrumentation techniques, technologies that keep our telescopes and others like SKA up to date and compelling science discovery instruments around the world. And I should say that in this talk, I'm going to give a few highlights scientifically and technically. There are more CSIRO presentations at this conference than I have slides in this deck. So I won't mention everything, but I think we've got plenty for you to see, and we'd love to talk to you afterwards as well. But let me start by giving you a brief tour around the ATNF in Australia. For those of you who are not yet familiar with this, we have an array called the Australia Telescope Compact Array. You can see on the top right, which is 622-metre antennas in New South Wales, north of here, operating from around 1 to 100 gigahertz. We have Murayang, the Parkes telescope, which is a 64-metre dish, which we've kept up to date since the early 1960s with new instrumentation, and you can see some of that at this meeting. We have ASCAP in Western Australia, which is coming to its stride as a survey telescope, opening up that quality of imaging of the whole southern sky in many different ways that will enable us to make best use of SKA and our other telescopes. And we also have the observatory site itself, which I'll come to on the next slide, which is where we're hosting the SKA project. And together we join telescopes in Australia and around the world into the long baseline array. And I'd like to acknowledge the traditional owners of all of the lands that we're working on in Australia, Inyaramana Ilgari Bundara, the Murchison Radio Astronomy Observatory, and all of the other sites and their own traditional owners, past and present. Here's an aerial photograph of ASCAP on the observatory in Western Australia. This is a place which was selected for its remoteness and radio quietness, where we're operating ASCAP, 36 12-metre antennas with novel phased array feeds to survey the sky, and we're also hosting the Murchison Wide Field Array, the Edges Experiment, and of course the SKA Low Telescope that you probably heard quite a bit about on Monday. The ASCAP telescope has a wide field of view to its phased array feed of around 6 by 6 degrees, and it has 6 kilometre baselines providing arc-second resolution at 1.4 gigahertz. Right now, it's engaged in a program of all-sky surveys for time variable sources, short and long spectral line and emission and absorption, continuum and polarization. And the earliest science of ASCAP, which I'm not going to talk about more on this, some of the most exciting early science was around fast radio bursts, and I talked about that probably at previous URSI meetings. In fact, there have been other talks in this meeting. The surveys will take around 5 years to complete. And so I've just got a couple of slides on some of the key ASCAP surveys that are underway right now. This is recently published work from the EMU survey identifying 3,500 complex radio sources associated with AGN. And here you can see some examples of bent radio galaxies and so-called complex radio galaxies that demonstrate the combined features of wide field of view to survey the whole sky and the imaging fidelity and high resolution. And the EMU survey will, of course, discover tens of millions of radio sources. And one of the other high priority surveys is the Wallaby survey, which is an H1 survey. And we've been here in this image, we've been combining the image from Wallaby with the image from data from ASCAP with the data from Murayang, the Parkes telescope, and the Australia Telescope Compact Array to show the potential for these different instruments to work together to provide the highest quality information about H1 and galaxies in our universe and the hydrogen star formation. And although the surveys will take us around another 4 years, we're not intending to stop there, and we are looking at what the technology is that could be used to make ASCAP a complementary survey telescope to our other instruments like SKA, even as SKA commences its operation early in around the end of this decade. The next generation phased array feeds will need to have a significant sensitivity upgrade, and the R&D is underway to both increase the sensitivity but also improve the operational ability of the operational situation of the phased array feeds from what we've learned from the site. For example, with new cooling systems and weight simplified maintenance. And you can see some of the technology from these out in the foyer. On Murraying, the Parkes telescope, we've had for probably around a decade now, we've been engaged in a program of replacing, I think, around a dozen feeds with 3 feed systems. The first of these is the ultra wideband low receiver, which is now our very popular and receiving system on the telescope right now, operating up to around 3 or 4 gigahertz. And that's a wideband, high sensitive single pixel receiver. And we're taking that technology, which uses the dielectric field technology that we saw this morning in one of the talks, to bring that up to 27 gigahertz and give you that high sensitivity coverage over the entire bandwidth. And we're complementing that with the cryopath, which I've got in the next slide. This program means that we won't have to do any manual receiver changes. All the receiver changes will be on the turret, so that will improve efficiency and reduce operational cost and improve health and safety at the site. The cryopath is a phased array feed derived from the ASC AP program, but brought into 3 dimensions. We call these the rocket path elements. They're also, as well as improving sensitivity, more amenable to cooling, cryogenic use, and that's what we're doing at Parkes. The prime focus to achieve better than 20K system temperature over this band and speed up the surveying for total intensity of hydrogen in the southern sky. That receiver is now on and off, and to be honest, on and off the telescope as we go through engineering commissioning. And we've got some exciting results that show us that it has the performance we're expecting. We've also got some cryogenic material that's used to work through before we can have that fully going for community access, hopefully around the end of this year. And along with all of other instruments, this will be available on scientific merit to astronomers around the world. And that's true even as we turn some of our telescopes to other projects where we might do space tracking, space situational awareness, where we use the telescopes to do new projects, but at the same time provide merit-based access for astronomy. Just a couple of days ago, we started to turn off the CAB correlator system at the compact array in Narrabri. This is a system that's been operating now. It's been our prime science system now for around 15 years. It has been very successful, coming as it did just after some major receiver upgrades, but the technology is old, the system's been failing, and we've had the opportunity to improve the performance, the reliability, the bandwidth, and the number of modes that we can offer to observers with this new system, Big Cat. And there was a talk on some of the technology for that yesterday. Right now, the status of Big Cat, as I said, we're decommissioning the old system because this is working. And on the next slide, you can see one of the first science images that's already been shown at this conference. Late this year, we'll be also changing out some of the other analog systems to double the bandwidth and begin observing later in the year for shared risk science and add further modes next year. This is IC 4296, an elliptical galaxy in Centaurus, and it's exciting to see this result. At the same time, we'll be completing a major infrastructure project because we see the possibilities for the compact array, not just to complement existing telescopes until SKA starts to dominate the mid-wave frequencies with SK Mid in South Africa, but also for other projects like space tracking and space domain awareness, by replacing a number of the systems which are now approaching 40 years old, and doing that in a way that enables us to improve performance for observers and also provide new modes and reduce our costs, simplicity of observing. One of the new science areas that the compact array is entering, and which is enabled by the reliability of the system, is around time domain science. We're doing a lot more projects in time domain science than we had been over most of the life of the compact array. And this is a nice result from a swift detected short gamma ray burst, which we're able to follow up within just tens of minutes from the detection, with the capability of this system now to respond very rapidly. And this, I think, is one of the areas that we see as being a really important contribution of the compact array in the next decade. Now, I'm not going to go in great detail into the SK low correlator and beamformer project, but there have been other talks on that system also. And perhaps you saw the system with the talk this morning, which was actually not given by Grant, but anyway, given by David. But we're very proud to see that system now on the SK low telescope used for the first fringe and the first image of SK low. And the technology here is shared, actually. All this technology is shared between our various systems on the various telescopes that we're operating and other ones building for others like SKA. Successfully now passed the AA.5 and the AA1 factory acceptance test, and we're currently working towards AA2. And this is one of those parts of the system which is in advance of the overall SK schedule. So we're certainly very happy to be contributing to the project. One of the projects as we look further forward that we're looking at is Lambda, the low frequency Australian megameter baseline demonstrator array. This is a project to demonstrate the potential of science from low frequency VLBI across the whole continent. Many of you will know that the SKA is being built across an area, an extent of around 50 kilometres in Western Australia, which means it will soon be the most sensitive low frequency radio telescope in the world, but it will not be the largest. It will not have that sensitivity over the very long baselines and the ability to image the highest resolutions. And we're aiming to snatch some early science by demonstrating the potential for VLBI at low frequencies in Australia. And I hope encourage SKA's investors and countries to grow SKA across the entire continent, which was the vision for SKA. It has been the vision for SKA since it began. Since the concept began, and something that I think we'll turn our attention to once the current telescope is ready. So this is the small prototype that's being built at Narrabri now. It's just a few tens of antenna. We might take that up to a whole SK station at Narrabri and nearby. You can see here some of the ADC module assembly and a simulated all-sky image with 36 antennas. And there were talks yesterday and this morning on that system. Finally, having talked about telescopes and new instrumentation, I just wanted to turn to archival data or the power of the past, because this is something that will become ever more important for radio telescopes, the quality of the data and the results that we curate. In fact, we've got tens of petabytes from CSIRO telescopes already, and this is going to be a challenge for all of us, is to maintain those data in the long time. But this is over the long term. But this is a really nice result from the receiver that's now been replaced on the Murray Parkes telescope, the multi-beam receiver, where this pulsar catalogue really is now showing the citations still growing even 20 years after the paper was first published. So you know, as we continue the impact of these systems will be felt long after we stop using them. And even as we look, say, to the ASCAP publication record and the ASCAP citation count, it's growing in a shape much more like this, quite different to the proposal-driven telescopes like Parkes and Compact Array. And version 2 of this catalogue, by the way, is being worked on at the moment with Lawrence Toomey and Agastya Kapoor. So finally, my summary is that the 18F is evolving. We are evolving to bring our telescopes and our instrumentation to the new global world of telescopes that countries need to make by joining together. Our own facilities will complement and support the period until SK telescopes come online, and some of those will continue on in the longer term with new missions. We'll also continue our instrumentation program. That's what's been driving radio astronomy here. And it's certainly one of our primary contributions to SKA, and we hope that will be so going forward. I'd like to thank the team at the conference, the whole team here, and I'd also like to note the fantastic relationship that we have with the Wadjuri Yamatji, the traditional owners of the site in Western Australia, where SK and ASCAP are. This is a lovely piece of art by Nolene Hamlet, part of the collaboration of the Shared Skies exhibit we've done together with SKO that shows the ASCAP antennas and the SKLO antennas on the observatory site. Thank you very much.
Douglas? I have one question myself, if I may. I noticed that for the choreograph for the partial scope, that using all the elements, well, for ASCAP, you have been using synthetic boards. So how do these compare? Do you plan also to use what technology do you plan to use for the ASCAP upgrade?
Yeah, so firstly, the original ASCAP design is a compromise design. What can you build and have perform for a reasonable cost, and their room temperature systems with some small amount of cooling. The transition to this three-dimensional shape was evolved after ASCAP, using a lot of the, I guess the development of the ASCAP program, but it's a new technology and a new design. Now, there are several people here, probably Alex is here somewhere. Saw him before, it's gone away now, but Stephanie will answer questions. Are you pointing at Stephanie? Yes, on that. So the design for the upgraded ASCAP is only just beginning, and we'll be looking at the three-dimensional path as well for that design. Probably will. Well, I don't think we're doing cryogenic cooling for that, but that's one of the choices that you could make. And the intent of this program is to keep that possibility for phased array feeds alive for SKA and for other telescopes of the future.
Yeah, great. Any other questions? Briefly check whether Ron has a question. He is online. Any notes? So then I suggest we thank Dr. Shen. Let's move on to the last week, 12:50. Schreef de heer Loris Nijmels, hoe schreef mensen naar de vraag van alles.
Well, good afternoon, everybody. First of all, I would like to thank the organizing committee for accepting our presentations. I'm going to be giving free. And this has been a good opportunity to visit Sydney for the first time. I'm very excited. I really enjoyed it. Thanks for the organization and thanks for being here. So this first talk is on behalf of our director, Sean Doherty, who is at this moment having very challenging discussions about our budget. He's not so far away from here, but he will not make it. So apologies on his behalf. And I'm going to give an overview about the status of ALMA during the last year. Since I'm not so sure about how many things you know about ALMA, I will just give a brief summary. So in a few words, not so this, yeah, okay. So we're the most advanced radio telescope in sub-millimeter and meter wavelength range. So we're a partnership with three as called executives. So the site, of course, of the observatories in Chile, northern Chile, we have the center of Santiago, Sat Santiago, but the data have been taken from northern part of Chile. And we have three ALMA regional centers, the ARCs. One of them is North America in Charlottesville, covering US and Canada. We have another one in Garching, close to Germany, which represents the ESON member states. And also we have another one at Metaka, Tokyo in Japan, which covers Japan, Taiwan, and South Korea. What you see in the yellow numbers is the participation of the budget from the executives. Of course, we're not having our own budget. This is coming from the executives. We have 37.5% coming from ESO and NRAO, and another 25% coming from NIMS, from the Eastern partners. And the time is not equally distributed in the sense that Chile has 10% of the time, and then when you subtract this 10%, the allocated time is distributed, accepting the executive balance between different executives. So this is a photo of our OSF. Luis, who has been involved in constructions, has in his memory something very, very different. It's a very quiet place now. It was not like that in construction. It's at 3,000 meters. It's a very remote place, of course, is very dry, obviously, or millimeter. We have quite some staff on the site, not so many as before, but we have around 250 persons on in total working on 2 shifts. The shifts at the site are 8 days at the mountain, 6 days off. It's 50-50 shared between the contractors and the ALMA staff. Of course, we have about 60-20 persons at Santiago premises, and we're taking very much care of giving equal opportunities. We have a lot of women colleagues, and we're very much interested in having more. And we're very sensitive about respecting the communities as well, of course, in the Atacama Delta. This is how the area operator site looks, the AOS looks like. That's at 5,000 meters. So ALMA consists of 66 parabolic antennas. They have unprecedented sensitivity and extremely precise pointing. We have the front ends and now have all of them are filled into 10 state-of-the-art receivers, covering the wavelength range from around 2530 to 950 gigahertz. And the great thing about ALMA is that we have 66 antennas, but we have about 200 pads to which the antennas can be relocated. So our observing cycle starts on October 1st, and it ends at the end of September of every year. So throughout the cycle, or between 2 cycles, the antennas will be moving around 1 antenna per day. So the array expands gradually and contracts, providing different angular in the sky, and can go back to 16 kilometers, providing amazing resolution of 0.3 arc seconds to the sky. Okay. What you see also in this photo is you have what you see there is our compact array. We have 4 types of antennas. So we have our 25 North American antennas, which are 12 meter, and together with the 25 12-meter European antennas, they comprise the baseline correlator array, or the 12-meter array. We have then our 12 7-meter antennas, which comprise the Atacama compact array. And actually, this is what you see here. The antennas are very close to each other. They're 7-meter. Distance between 2 antennas can be just 2 meters. So we have to be very, very careful every time we do any antenna moves. We don't want to damage anything. These are very expensive toys. And we have 4 12-meter antennas for total power observations to cover the zero spacing flags coming from the sky. And this is how the antenna has been moved. So as you can imagine, during the construction phase, the antennas were being assembled at the hangars of at 3,000 meters. They have to be relocated to the AOS at 5,000 meters. That's a 40-kilometer drive. It takes about 8 hours. You can walk next to the transporter, actually. The transport itself weighs 120 tons. The antennas another 120 tons. Now that all the antennas are the high side, we relocate them. So I said, from about 1 day, the transporter has to take 1 antenna and put another pad so that we can change our configuration, meaning that we're changing our angular resolution. Now, let's go to the report itself. So we're very happy to present these numbers. What you see here is the number of hours in the sky as a function of time. The observing cycle starts, as I said, on October 1st. So we're extremely careful about how we take data, we do a lot of quality assurance. So what you see in the continuous blue line is the hours in the sky we've collected until now. Our goal is to collect 4,300 hours in a single year. The green line that you see is what we had been scheduling based on number of scheduling blocks that we have been collecting based on the proposals that have been accepted. So we're 300 hours above the projected time on the sky. And the orange one is the curve that corrects for maintenance and other effects. So really doing very, very well. we have learned a lot of things in the past years. November and December 2024 have been the most productive months of observations ever. We have collected more than 500 hours observations per month. And the observing rate is consistent with previous 2 cycles. So we have been repeating our successful productivity, and we're very happy also to continue working to maintain the area as productive and operational as possible, considering that we have had major snowstorms. What you see in with the vertical lines here is storms and some outages of the power, unfortunately, and some other tactical events, but which do not have such a major impact, considering that we have managed to recover that time loss. Well, this is a photo that shows the reality of the observatory at 5,000 meters when you have windstorms. It's a shame that although Sean gave me a video, I could not put it on PowerPoint, and for some reason it was just black. But it was a video, that was really showing from a vehicle during a windstorm and snowstorm, recording what's happening. It's really scary. Obviously, these are very hard conditions, and probably you don't know, but at 5,000 meters, we're not the only observatory. At the plateau where ALMA is operating, we have what we call Astronomical Park. There are several observatories there, and from time to time, we have to go and, I will not say rescue exactly, but provide support to colleagues who are stuck there, and they cannot just come down so easily. So we have an experienced rescue brigade at ALMA. We're taking very seriously safety measures. We have continuous training, and the fact that we have teams who are operating 8-6 at the mountain on regular basis keeps them acclimatized very, very fast. We have had a fatal accident. Unfortunately, this happened years ago. It was not from our staff, from another observatory, and the police were not capable to recover the body fast enough because they were not acclimatized to work at 5,400 meters. These are the extreme conditions we're facing, which shows how amazing it is that ALMA is being able to take data at such a good rate and produce so many results. The snowstorm is over. That's what you get. And of course, this is not snow which is easy to take away. So a lot of manpower and engineering is requested to be able to recover the array as soon as possible. And as I mentioned before, our extended baselines go up to 16 kilometers. So imagine trying to maintain those paths, which are so far away from the main array, operational. Okay. We don't have antennas always there, but when you go to baselines of a few kilometers, it's always a challenge. We don't compete with any other observatory in this wavelength range. We compete with ourselves. So we have to be very careful about how we're spending our time. So what you see here is the expected amount of available time for a 12-meter array, and how from the blue line, we start dropping the available time, which you see it in different boxes of red color, considering first we have to do engineering activities, and then you have to provide EOCs, the extension of capability. So for every new observing cycle, or providing new capabilities to the community, which means you have to test data. So you have, of course, take away time on the sky from PI science for getting those data, and also preparing for the next observing cycle. So we take away those hours, and of course, we have to do the February maintenance. At every February, we shut down the observatory. We have, although it's southern hemisphere and it's summertime, there's a very particular climate, which is called Bolivian winter. A lot of snow, a lot of rain. The observatory takes advantage of that microclimate and shuts down completely. We don't take data in February. And your annual maintenance. It keeps us busy the whole month, but then we're up to speed and able to perform very well, starting from March on until the next shutdown. And then you continue reducing time, etc., etc. Of course, you have to do software testing. We have a regular observing cycle of, but also software has to be updated to need to take data for the new observing cycle. We have to consider scheduling downtime, etc., etc. So at the end, what we have is this number, which is about 4,300 hours per year with a 12-meter array. For the ones among you who are radio astronomers and are very excited to use the higher bands, so band 9 and band 10 in the highest frequencies, we have been very, very careful about allocating time when possible, when the weather conditions allow. I mean, we have a pressure factor of about 7, so 1 out of 7 proposals have been accepted. But even among the proposals that have been accepted, there's a lot of pressure factor for the specific local signal time LSTs, right? So projects compete with themselves. So it has been decided that whenever the weather conditions allow, the highest priority will be given to band 9 and band 10 observations. One criteria would be, for example, I have a project which is 90% complete. I want to finish that project, and maybe it's a band 3 or band 6. No, that project might not be completed, but priority will be given to higher bands. This has been agreement for a few years, and we are committed to taking more band 9 and band data. And the last 2 cycles have seen this consistent band 10, where the conditions have been very similar, but have a small improvement regarding the number of hours taken for band 9. And what you see here is the hours of observations as a function of time. Every bar is a month. Different colors are different cycles. And what you see here is roughly, same performance in the last 3 cycles for specific months. So very happy to see that we're able to reproduce high numbers of observing times during specific months when the weather conditions allow us to do so. So reproducibility. We have had a very unfortunate event with the cyber attack, which was very, let's say, aggressive and had some, damage. Of course, we could not take data for about a month, but we recovered from that and have improved our cybersecurity and enhanced it significantly together with our partners. So what you see in this plot is our cycle 12 call for proposals. So the number of proposals is still very, very high. It's a small drop in the last cycle, but of course it's still, significant. And what we have, what is called large programs, I mean, just more than 50 hours of ALMA time. It's still, number of proposals is steady, of the order of 40 something. Okay, we're very happy to see that. And as I mentioned before, the pressure factor is about 7. And we're still doing great science with all the proposals which have been accepted and have been observed. So what you see here is the breakdown per array type. We have 3 arrays, as I mentioned before. We have the 12-meter array, 7-meter and total power. And this is how much time has been requested for the proposals. So I have 30,000 hours requested for the 12-meter array, and about 16,000 hours for the 7-meter, and about 11,000 hours for the total power array. And that's the oversubscription rate on the 12-meter array separated by region. So the astronomers around the world are registered in our portal, and they are identified as users through one of the regional centers, North America, Europe, East Asia. And then you see how every region or different regions is asking for, proposal time. And this you see is the oversubscription rate. So North Europe, for example, has a pressure factor of about close to 8, North America close to 7, and altogether around 7 as well. So it's still, after so many cycles, ALMA is extremely appealing to the community for taking data in the sub-millimeter wavelength range. And this is a graph that shows the publications. So the horizontal axis running time of the facility since its commence, since its start. So the vertical axis gives the number of publications per year. So Spitzer and HST, of course, are the champions, but these are space observatories. And ALMA, together with VLT, are the most productive ground-based facilities worldwide. Okay. And connecting the previous presentation about the importance of archival data. So what you see here is the ALMA publications as a function of cycle. The blue line is just the PI signs. And so ALMA has a 12-month PI policy. So the data belong to the PI and its collaborators for a year, then they become public. And we're very happy to see that the community is using more and more archival data. The treasure that we have in the ALMA archive is just precious. So I encourage the community to use those data and not just ask for telescope time. There's so much information in the archive. We have petabytes of data that can be used for doing amazing science, of course, combined with other facilities. So we have had until now almost 4,400 something referred publications. And the PNU publication rate has increased in 2024. And as I mentioned before, ALMA is a leading producer of publications among ground-based facilities. What's coming next? What's coming next is a presentation of mine, actually, about this. Okay, so the future of ALMA is the wideband sensitivity upgrade, the WSQ. It's a very ambitious and challenging development program that will enable ALMA to stay active, productive for the following decades. The goal of WSU, as it's called wideband sensitivity upgrade, is to upgrade the IF bandwidth by a factor of 2, hopefully, if the budget allows, by a factor of 4. And when you upgrade the IF bandwidth, this means you have to upgrade not only the whole signal chain, but also the software and the associated hardware, which means the front ends, your back end, the correlator will be a different correlator. It's going to be like a different place. I'm not going to give more information now. The processing is going to be much more challenging. And of course, not only the software part itself, but all the infrastructure related to processing the data. And of course, how you store the data. ALMA has a policy where we have an exact archive of all the data at every site. So we have the central archive at Santiago and an exact copy in each archive of the executives, one in North America, another in Japan, another in Europe. So there are 3 identical copies. So when you increase by a factor of 50 your data, it's a big challenge, starting to transfer the data and maintain the data in the archives, which becomes, of course, expensive. Obviously, we want our astronomers to have the best experience possible. So we have to think about, as part of the Archive 2030 vision, how they're going to make the best use of the data we are collecting and will be collecting in the following decades. And that's part of the challenges we have in the ALMA 2030 development roadmap. So the talk about the preliminary design review, preliminary design is at 4:20, and I'm going to talk about the preliminary plan of AWSV at 16:40 if you're interested. So that's all. I will thank you for your attention. The highlights is that ALMA is observing at its highest efficiency. We published 560 papers in the last year with usage of archival data increasing. We have our oversubscription factor of about 7, and wideband sensitivity upgrade is on its way. It has already started, and it's going to continue for the following 10 years approximately, and will enable ALMA to continue being one of the most powerful, productive astronomical facilities for the next decades. And of course, before ending, I want to thank our colleagues everywhere around the world for maintaining ALMA such a productive tool. They're constantly working in different aspects, development, operations, support, software, support the community to maintain ALMA at this high level of efficiency. So that will be all. Thank you very much for your attention. And look, I'm ready to take your questions. Thank you.
Thank you very much. Are there any questions? Yes, please wait for the microphone.
That's fantastic summary. Thanks very much for that. What I suspect is a simple question that I should know the answer to. What was responsible for the huge jump in large proposals between cycle 7 and cycle 8? Was that a policy issue or allocating time to large proposals, or was this something else?
I don't have the answer to that. I don't have the answer to that. Yeah. Yeah. Okay.
It's fascinating because the jump by a factor of 3.
Yes.
One cycle to the next, and then
Yes.
stay.
Yeah.
Thank you. Are there any other questions? If not, then let's stop the session here. Thank you, Doris, again, and see you all further.
Yeah, sure. I think what happened, I was struggling to, because I was already out for 4 cycles, but I think there was